Hi, this is Sarah with Lab 9 on spring. The problem in this lab was to analyze the 2D motion of a spring, and the system was the spring, the mass, and the earth. The main result was that my model fits my experimental data very well. Here's the video that was provided to us. I put the origin where the spring is attached and calibrated it at the equilibrium distance of 0.7 meters. Then I tracked the motion of the mass and plotted the x and y positions as a function of time. And here is the oscillations up in the corner. I defined some of the initial values for this, such as k, so I experimentally found the oscillation period, which is 2 pi over the square root of k over the mass, which was given to be 0.402 seconds. And then I solved for k, and it ended up being 6.913. Just a summary of initial values. K, I just showed you that I found. The relaxed length of 0.13 was given, and then the x and y periods of oscillation were 1.581 and 1.621 respectively, and I'll talk a little bit more about those later. So I proved that the relaxed length was in fact 0.13 using the spring force equation. F equals Ks. I knew everything except for S and found that to be 0.569, and then used S equals L naught minus L and found that L is in fact about 0.13 meters. The main concept in this lab was the energy principle, which is the sum of all the energies equals work. The energies in this lab were kinetic energy, 1/2 mv squared, potential energy of the spring, 1/2 ks squared, and gravitational potential energy, which is mgh, and h is height. Here's my model. I put in the correct mass, which is 0.02, and then I put in the initial position that I found in Tracker. This is important because these systems are very sensitive to initial conditions. I used the momentum principle to update the position, which is right here, and we've done that a billion times in lab. And then here is all of the energy principles that I just explained to you, the KE, UG, US, and works in there too. And then I plotted delta kinetic energy, change in gravitational potential energy, change in spring potential energy, and then the sum of all of the energies in the system, which equals work. So when you run it, this is what you get. The blue ball is my experimental data, which you can see is sticking quite well with the model, which is in orange. My graph over here is all of my energies that I plotted earlier. The blue is the kinetic energy, the green is the gravitational potential energy, the spring is in red, and the yellow straight line right there, constant as 0, is the work, which is the sum of all of the energies put together. As you can see, my ball is sticking really well with the other one, meaning that it's a very good match. So what does it mean exactly, comparing the x and y periods of oscillation? Well, I graphed the x and y positions with respect to time and found the period by comparing the peaks. I found the period of oscillation in the y to be 1.62, which is higher than the x period of oscillation, 1.581. This is because there was initially more displacement in the x, so it would be going faster and therefore have a smaller oscillation period. Okay, for the second question, determine the work in the done by the surroundings. Well, the system is the mass, the spring, and the earth, and nothing's really interacting with the spring, so there's no work done on the surroundings. You can see this if we pull up the energy graph. Work is the sum of all the energies. The sum of all the energies is this yellow line, which is constant and at 0. Potential energy is the negative of work, so if the spring had been outside of the system, work would have been done by the spring, but we account for that by adding in the potential energy, so delta E is equal to 0. For the third question, we changed the origin so that y equals 0 when the mass is at rest at its static equilibrium state. If we go back to my model, here I changed the origin to 0 and then 0.70 and ran the model. As you can see, it makes dramatic effects to the y position, and also you have definite changes in the magnitude of the kinetic energy, potential energy, and spring potential. However, work is still constant there at 0, and the sum of all of the energies stays at 0. Notice there's almost no change in the x direction, but profound change in the y direction because we changed the initial y condition. Thanks for watching. Beasley has